So the topic of columns starts, it is amazing, but starts with, a study on the equilibrium of a part. So basically, so we have seen so far that, okay, we want to understand when something is, not when, but, what makes a part fail. And we have seen that from the point of view of that, some stresses are going to be larger than the strength of the material. Or we also said that, okay, or the part is going to deform beyond usable limits. So we have seen that part or the failure of components under those two lenses. Now, when talking that, it is very clear from those let's say points of view that you are comparing two things, and if one thing is larger than the other, well, this is what's going to happen, and the failure will occur either because it deforms or because it breaks, suddenly breaks. Now, yeah, in bucklings, when looking at buckling of columns, it's not a different kind of how they're going to fail, but the mechanism on how they fail is the big difference from all of these. So, and everything starts from the equilibrium consideration. So let's look at this chart or this graph. So first we have three stages of what is called equilibrium. You've seen that maybe in other disciplines, in other topic, or sorry, courses. But you have in equilibrium, you have what is called stable equilibrium in this sense here. Basically, you just put it there. So if you have a small sphere, a ball, and you just let it run here and you just release it here, so it's going to just be oscillating until it finds its equilibrium position. And if there are not any other forces applied to it, it means that that would be staying in that position no matter what, and that's considered stable equilibrium. Now, let me jump at this one. Unstable equilibrium is that, yeah, maybe at that position here, and I hope that you can see the highlighter on the mouse that I'm using, because I realized in the previous videos that it was pretty difficult to follow up what I was saying because there was not any indication where I was pointing at, but hopefully you can see it. Is that, yeah, in this position is fine. However, if this sphere or ball rolls a little bit to the right, it will just fall down. And the same happens to the left. It will just fall down. So that's what is called unstable equilibrium, because it only needs a little bit of something, a force, to produce that this ball will just be lost. In this case, in the stable equilibrium, the sphere, even though if you apply another force or systematically apply some force, this is always going to come to find the stable equilibrium. Now, this is the big difference between unstable and stable. In between those terms is the neutral equilibrium, where it just says that, what, I'm here, but if you apply a small force, let me just draw force here to this sphere here, so that sphere is going to just move to the other direction, and that's fine. But as long as you remove the force, and provided that there is certain resistance here, so this sphere is going to kind of stop at some point, and that's it. And then when you apply it again, another force, maybe in the same direction you applied later or before, sorry, then this sphere will start rolling again until you remove the force, and then due to the friction appearing in the contact between the sphere and plane, so this ball will stop again, and so on. So that's called neutral equilibrium, and these three stages are greatly represented by this chart here. It looks pretty fine that depending on where this sphere is located along this axis here, then you will find that this sphere would go from a stable equilibrium to a unstable equilibrium, crossing the line of neutral equilibrium. And columns fail in that fashion. Here is a brief example of what would mean to have these three types of equilibriums but applied to column failure. And in the first case, when the equilibrium is stable, then the column would stay straight up and nothing would happen. Everything would be fine, as we hope to see in many of the structures we inhabit or we lived in, or we walked in, or anything. So if we go to a building, we would like to see the columns to remain straight no matter what's the law applied to the well, according to the design, to the structure. So this is the case we would like to have. So when the force applied to the column is less than certain force that we are going to start calling later as crippling force, meaning that that's a force that, while this force P remains smaller than this PCR, which I'm going to call crippling force, and that comes from the column terminology, or you are going to find it represented as a buckling force. Then while the load applied to the column remains smaller than that PCR, crippling force or buckling force, you can consider that the column is in stable equilibrium. When that force matches the value of the crippling force, like in this case here, it's like imagine you're having a small piece of a small rod, and then you apply the force, and then you deviate, kind of you move a little bit the application of the force towards one side, and then suddenly you're going to see that the vertical rod, is not going to hold still, because it's kind of the equilibrium. If you apply the force a little bit here, so it's going to increase the possibility that the column will deform in certain direction, and you don't know in which direction. Well, I will tell you later in which direction the column might probably deform, or say create this inequilibrium, but that's something that starts happening. And definitely when we're talking about unstable equilibrium, it's because that force has becoming larger than the crippling force or buckling force, that the column is that is going to fail. So I said that this is amazing because the concept of studying columns stems from studying equilibrium. And even though that might seem a little bit complex to the topic, we're going to realize later that the formulas we use to calculate columns, not to calculate columns, to say if a column is probably going to buckle or not, they are very simple. They are pretty simple. And you're going to be surprised that one of the theories we're going to see here in the course is a theory provided by Euler about 300 years ago, and we're still using it. So that's amazing for me. So, and that kind of reinforces what I mentioned in our first class, that the body of knowledge of mechanics of materials or strength of materials is so established that it is something that you can find anywhere. So that's why I don't recommend any specific book or anything like that. So you can find it anywhere. It's very proven in that sense. Let's take a look at this. Why, kind of more in details, why columns would fail. You see here in these two pictures a couple of column failures. One that seems to be metallic and one that seems to be built in concrete. And both of them, they fail. So we know, for example, that concrete is very good to be used when compressive stresses are present, because the compressive resistance strength of the concrete are wonderful. The tension resistance of the concrete are lousy. So this might be that the buckling produced in this column was such, that's my assumption, was such that the tension strength was overcome by the forces applied here. In this case, you see a typical buckling of the column, and I might have skipped this, but let's consider the buckling. The columns are those elements, like I'm presenting in this one, which are vertical elements and are loaded in the actual longitudinally, actually. So meaning that when we are referring to columns, we're referring to vertical elements. We have an actual load here, and that's kind of what we are going to call as columns. You are going to find in textbooks also that the study of columns comes also along with the study of struts. And struts are, in a sense, columns, but they are set just not to be oriented vertical, meaning that if you have a structure like this one that we have seen, in many roofing structure, that you have these kind of elements like this, and then you have this is because this is holding these are a couple of columns here, and then it's kind of a warehouse or something that you are designing here, and then you have these kind of structures here. So these elements here are called struts. And actually, when you design this kind of, let's say, configuration, these struts are positioned in a way that they only work in either tension or compression. So that's why they're called kind of struts. But they are basically using the same logic approach for failure as those used in columns that you would find, design of columns or design of struts. So you can see here, kind of again coming back to this column buckled in the sense, and most probably was because of the load applied, overcome the crippling load of the column, and then it buckled. And this is the natural way columns deform. This is the natural way columns deform. There is no other natural way. So, well, they might be other natural ways, but this is the most likely natural way to fail for a column. And why they might fail? Well, we're going to see that in the failure theories soon to come, that it might be because the column was not straight, was not uniform. So this axiality alignment between the actual loading and the, let's call it, centroidal axis of the column was lost. And then when you lose that, let's say, alignment, then you say, well, the column is not straight and uniform, or it was bended initially, or this is very load was applied centrically. That is very related to to also the type of failure when the column is not straight. Problems with the material, it's not homogeneous. Some issues in the manufacturing process of the material, or basically, well, these three elements are now kind of realizing that number one, number three, and number six is because the column is not straight and it's not aligned. The forces are not aligned with the centroidal axis of the column. Good. Questions so far? The first theory we're going to look at is Euler's theory, and this is the one that I mentioned that comes back from the 1700s, 17 something. So imagine that 300 years, and we're still using it. And it is not that newer theories have come, but it's still valid. Euler buckling theory is still valid. You might see that, yeah, it might be replaced by other type of theories according to standards or tests for different type of constructions, but this is still a pretty valid theory. And before jumping into mentioning what are the assumptions that Euler took into account to formulate this theory, I'm going to walk you through what is our kind of a column classification system. And that column classification system is going to be essential to determine which theory might apply to a certain column depending of kind of if the column is considered a short column, if it's considered a medium column, or a long column. And the way to determine what's the kind of the classification of the column you are using or you are calculating is based on the slenderness ratio, which is again a geometrical figure to determine kind of that relates the length of the column with the radius of gyration of the column. And the radius of gyration of the columns is related to the inertia properties of the area and the area of the column. So when you calculate this slenderness ratio, and that slenderness ratio falls within one of these categories, then you can know how it might be possible that this column might fail. So what would be the failure mechanism of the column, for example? If it's a short column, you need to be concerned of crushing stresses. Crushing stresses is no more than having for example, imagine this is a column. Let me try to write something decent. And then you have a force applied. And then this crushing stress is no more than, say, well, imagine that this has an area. Area A. And then you say, well, the crushing stress, let's put it that way, crushing, well, just to differentiate it with the other. This one here equals kind of what we have seen, the force divided by the area. Because it's going to crush, it's going to make this column, kind of crumble in some of the sections there. So that's why it's called crushing stress, and shear columns are said to fail because of crushing stress mainly. When you are in the presence of medium columns here, then there is a decision making to do here. So it's kind of okay, well, it might fail by crushing and it might fail by buckling stress. Buckling stress is the stress created when the column deforms in this way. So when it deforms like this, it generates a bending inserted along the longitudinal axis of the column, meaning that in each height of this column, there's going to be a stress created by the bending of the column, and that's going to be called the buckling stress. Then, if it's a long column, it is said that would definitely fail by buckling stress, mainly by that. That's going to be the primary mechanism of failure. Now, important things to remember are slenderness ratio is a measure to classify if a column is short, medium, or long. And the slenderness ratio is calculated by the ratio between the length of the column and the radius of gyration of the column. And the radius of the gyration of the column depends on the area and the inertia properties of that area. Great. Now, let's come back to Euler's buckling theory. So there are 7, you can find 8 of the assumptions, and they really simplify the way columns are designed that way. So first, remember that I said that one of the main failure mechanisms could be, well, that the column was not straight. Well, Euler considered that the column was perfectly straight and the load was applied actually, meaning that this was perfectly aligned. This was vertical straight, and the load was applied just actually to the centroidal axis. So an ideal condition. You as an engineers in the work field, you're going to see that this is far from ideal. You're going to find it far from ideal conditions. So, but this is the assumption considered by Euler at the time. Second assumption, the section of the column was completely uniform, meaning that it was also an ideal case that the area was perfect, was the same along the whole axis of the column. Material obeys Hooke's law, and when it's referring to that, it means that we are going to be working in the, let's say, in the proportional phase or part of what Hooke's law says. Something like this. So if we represent Hooke's law by what is the stress and the strain. So we're going to say that we're going to work in this proportional part here only. Just imagine that it's going like this, taking a ductile material, and then we're going to say that this is only the part that we're going to be using, or we're going to consider that our element is going to be working here. Length is very large compared with its lateral dimensions, and this is kind of this is a very interesting comment, because from an engineering point of view, you always have to ask, well, what's the correct ratio between length and lateral dimensions, meaning that if I come back to this figure again, so this dimension here, which is the longitudinal dimension, is considerably larger than this one here, which is the lateral dimension. So, but how much is that? So how much should it be? Should it be, what's the ratio that determines everything? But even though it's not clear under the assumptions, we're going to see that that has a lot of relation to the slenderness ratio. And we're going to see something very important in a few slides ahead, that it's going to tell us, yes, you can use this theory for this column, or no, better you don't use it for this column. The other one is that column fails by buckling alone, and then that starts giving us a hint about Euler's limitations, basically. So if I say that columns fail by buckling alone. And if I look at this slenderness kind of column classification, and I know that, hey, something is happening here. So I know that from these three types of columns, the median column and the long column might fail by buckling stress, meaning that it, it is giving me a hint that Euler might be only applicable for these two cases and not for the case of a short column. So here starts the limitations of Euler's buckling theory to build up, in the sense, well, it might be, it might be used, but I may not be able to use it here. And also that's going to give me the hint that if I'm going to apply a theory, a buckling theory or failure theory for columns, maybe it would be wise to make sure at the beginning of the problem, at the beginning of the solution process, to make sure if that theory falls into the category it should be falling. So meaning that if I should be using, instead of applying the whole theory and then later on, finding out that that theory was not convenient to be used there. Sixth is kind of axial stress. It's very small compared to bending stress, and that's kind of reinforces the point number 5, because it says that axial stress, which is a crushing stress created by the vertical load applied over the area of the column, this crushing stress is considered to be way smaller than the buckling stress produced by the bending, of the part. Meaning that again, this is reinforcing the fact that Euler is working only for buckling stresses or long columns or medium columns. But there is a gray area here that we don't know which, if some columns so close to 32 of slenderness ratio can be used, or we can calculate those columns using Euler theory or not. So this is something very interesting, and that's kind of also reinforcing some of the topics. And then, he said that, what? Well, I'm not going to consider self-weight, so it's ignored completely. Questions so far? Good. Let's see how this Euler theory started. Here, I'm presenting you a column that has this cross-section, rectangular. This column is, we're not going to consider that at the moment, but this is important to emphasize that when you join a column to two other elements, being the ground and other, for example, a beam, there are ways that we have classified joining that column to these other two elements. For example, ends, if you consider this the ends of the column, I'm going to write it down. This is one end. And this is another end. Then it could be that both ends are pinned, and a pinned end, and we're going to see later what is that, or both ends are fixed, like it seems to be happening here, or one is fixed, the other is free, or one is fixed and the other is pinned. Those are the cases for functional columns in terms of ending on how they connect to the other two elements here. I have a kind of a reference system, XY. I have a length of the column that is called this L, as it is measured right now. It is called the free length of the column, meaning that it just considers physically what you're going to have as length of a column. And I want to make this distinction because later on in column design, you're going to see a concept of effective length, which is going to be depending on the length of the color, but it's going to have a variation depending on how the ends are used there. So that's why it's important to determine that, or to specify that this L, as it is presented like here, represents the physical length of the color, something that you can measure using a tape measurement or any other mechanism. Then for the case and explanation, we're going to have that this beam has a load applied, and kind of as an example, as a general example. If I extract this column to an individual element, And I said, well, you know what? This somehow, follow along with me. This load P is going to, besides loading the kind of the whole section, but we're not considering that at the moment because as this is the Euler's representation, we are saying that this column is going to be only subjected to buckling stress caused by the moment here. So if this deforms in this fashion here, so I could say that the moment created by this deformation at this point can be determined using what is called the Euler's Bernoulli formula, or the typical, or what is called the traditional, not the traditional, but the engineer's formula for deformation. I don't recall the name correctly, but this is a very well-known formula about, how to calculate a moment on a straight beam. And remember that this is also the same formula we use to start off the procedure to derivate what was curved beam. So it's very well known, a very well-known formula in that sense. So this moment can be calculated taking into account, how long it deformated from here, and also kind of, well, that's something that is kind of simply said how it goes. Then there is a mistake here, but in the end, this should be y. This moment is kind of produced by this force, which I equal here, and then I end up with this system of differential equation system of degree 2, second degree equation differential system, differential equation system, or system, no, differential equation. So this second degree differential equation, as it is postulated in here, coming from this graph, has a solution that is very well known, and it is something like this kind of. It is a solution based on trigonometric functions. When you find the solution of this second degree equation, you're going to find it, in this form. Then you're going to have A as and B as integration constants. That the only work that you need to do right now is to identify what's the value of those constants. And then this starts giving you another hint that if I know that constants in integration processes are found out by taking into account boundary conditions, and then I'm talking about ends, then it might be possible that depending on how the column is joined to the other two elements, it's going to affect the outcome of this formula here, and it does. Let's take an example. Well, I went ahead too fast. So when I mentioned in here that this is the most probable way that the column would fail is because when trying to look for the solution of the second degree equation solution in this second differential equation solution, this one, it might be possible that you have a deformation shape that resembles this one, which is the original case that we consider to start the formulation, or this is also a typical solution, or this is also a solution. And it just continues infinitely kind of to resemble this kind of shape according to the trigonometrical solution you're having here. So these three cases, at least presented here, can be a solution to the problem we are presenting right now. So this is important to know, and you will find out in text that this is introduced as a way to let know that what, it could fail like this, but columns are simple elements, and as many material will fail in the way that requires the minimum energy to fail, meaning a column, if it's most likely to fail in this way because this is what requires the most minimum energy in that sense, then it's not going to fail like this or like this. It's going to fail like this, because while this bending starts increasing here, it's going to come to a point that this is going to just give up, and then it's going to just fall down. So this is not going to happen, not even this. So it's not going to have time to happen to let's say, to occur this kind of phenomena. Not for a static solution in a sense. Questions so far? Now let's consider the end when both ends are pinned, or you can find this pinned word also used as hinged, kind of when you have the door, any door that have hinges, or basically, then this is the way is kind of is connected to the other element or other body. In this case, you can see both cases, a column joined to the ground using a pin end, but imagine that both in the bottom and in the upper part, they have these pins, so that's why it's called pin end. And what it does when you use pin ends on a columns, then what you're doing to the connection between the column and the other two elements is freeing the possibilities of movement of the column, meaning that instead of having restrictions for relative movement between the column and the other element, you are saying, you know what, if you use a pin end, this column would be able to rotate around these connection points, meaning that if this column here, if I let go the upper part here of the column, this is going to just, let me put another code. This is going to rotate towards one end or towards another end. The same here. This is able to rotate to this end or this other, if the upper part is cut. And this is what's happening here, because now I have this freedom. This is a freedom of rotation. It's not a moment. It cannot have a moment because it is free to rotate. Then there is no moment appearing here, when I do this free body diagram. Same happens in the bottom. Then if I postulate the, yeah, if I postulate kind of the solution to the second degree differential equation, is going to take this form. And to solve this form, meaning to find out what are the values of these constants here, I need to take into account the boundary conditions as mentioned. So the first boundary condition appears here is that when x is equals 0, taking into account that this is the 0 point, this is 0, 0. Then, when x equals 0, y equals 0, meaning that there is no deformation here. And then the second boundary condition would be that when x equals L, and then important here, look at the L we're using here. When is what is L, then this is also going to be, the deformation is going to be 0, because as it can rotate, so it's not going to go anywhere. Using these two boundary conditions, with the first one, I find out that the value of the constant A is just 0. And using the second boundary condition, I found out that I have this product of this whole thing. Now, if I have this whole thing, I have two possible solutions. The first one is that either B is 0, or the term kind of enclosed in these parentheses is also 0. So in any case, if B is 0, or the term of enclosed in these parentheses is 0, then it's going to be the solution to this equation, or to this equality here. But if I say that B is 0, which is a trivial solution, it is not correct so far, because we know that if it's just going to deform in this way, then saying that B is 0 means that y is 0 all across the longitude of the column. Then this is not possible to it. So this is not going to happen. This is not the answer. Then I need to look at the answer in this way. Kind of, I need to know what makes the sign of this term here equal to 0. And then if I say, well, if I want this to equal to 0, then sine has to be equal to 0, or sine of pi, or sine of 2 pi, and so on. Which means that this internal element is going to be 0, pi, or 2 pi, and so on. And considering one of their, 0 cannot be, because let's say it's not a value, but the most reasonable value for this to happen is that the kind of the solution to this is pi, and this is related to this one here. Remember, kind of the solution for the element, how it deforms, is equal to pi. And if I say that pi, so to construct this, that the solution is that this internal, what is in the fraction, equals to pi, and then I just take or solve for P1, which is the force applied to the column here, then I'm going to end up with this relationship. So this relationship, again, comes from just equating this equals to pi. And this is the what is called the crippling load according to Euler. Meaning that at this point is when the column will start buckling. It is a pretty simple equation that is still used, with the difference that this L that I'm mentioning right here is very different, or might be different than the L, which is the length of the free column, or the physical length of the column, height in that sense. So this is something interesting what we're going to see later. Now it's represented as kind of lowercase l, but it is an interesting concept here. Questions so far? Let's look at a second case. What happens when one end is fixed and the other end is free? And one representation of what could be a column that has one end fixed and the other one free is like this, maybe water tank. And we can see, water tank, so this is free to move wherever it wants to move according to the forces applied to it, but in the bottom it is completely fixed. And we have seen this kind of structure, so this is a very well possible scenario. Applying the same methodology here, so I have a column straight position, but it can deform like this. Then I can start postulating or writing the equations of moments produced by this force here. And again, it's going to be a pretty similar formula, but the difference is that, the force or the bending is going to be not only produced by the kind of the distance from the vertical line to where the column is located, but also for, where in the x direction, in the x axis, I'm measuring this y kind of thing. So basically, if I said that kind of what's the moment here created by this force, then is going to be the difference between this point of application of the force and where I'm measuring that. And that's a valid concept. If I continue kind of developing, derivating this, just have simple mathematical equation operations, say multiplying this times this times this, and then reordering the material modulus and the moment of inertia of the product of the element of the material, the section of the column, then I'm going to end up having this type of formula, which is pretty similar to the previous one, except that it doesn't have the term d located at the end. Now I have an equation, solution of a second degree differential equation here, where we are going to need to use boundary conditions to find what are the values of these two constants here, intervention constants. And again, I have this first boundary condition that says that, okay, when x equals to 0, right here, this is my point 0, 0, then y is going to be equal to 0. There's not going to be any deformation. But in here, you want to set x equal to L. I don't know how much this d can be. So I have no idea how much this can be. So that's why, for me, I need to jump to another level and say, but you know what? I do know that when x equals to 0, there is not going to be the angle that the beam forms with respect to the vertical line is going to be 0. And that's represented here. Kind of, this is just representing that kind of, what's the angle here? And at that point, that angle, let's call it theta, is 0. This is a name. So that's what I can say. Great. But then it means that if I use the first boundary condition in here, then it's going to happen that A is going to be equal to minus D. Well, basically because this is going to be 0, this is going to be 0, and then, well, this is going to be 1, and then, A plus D, so A equals minus D. That's the kind of the result here. But when I try to use this equation, I only have this equation here. And they're asking me for the derivative between, between y between with respect to x, meaning that I have to take this equation and calculate the derivative of y with respect to x. And that's what is done here. So when you make that derivative here, so you're going to find this equation here. It'll be kind of lengthy equation, but it's the kind of product of derivating this. And at that time, when you apply the boundary condition, then two things might happen. Is that either b equals 0 or this equals to 0. So for this equation to be equal to 0, so at least one of those two conditions have to happen, that this equals to 0, or this equals to 0. That's it. If b, well, first, we know that this is not going to be equal to 0. And the reason for that is that L, if you have a column like this one here, is definitely going to have a length, a height. There's going to be definitely a load applied, and that column is going to have also section properties. Then this cannot be equal to 0. So what I mentioned here, that 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 this is kind of, this might be 0 or this might be 0. So it turns out that, you know what, this can never be 0, because they are based on physical characteristics of the column construction, geometry and loading. So this cannot be equal to 0, but this can be equal to 0. And then that's the kind of the only solution possible for that equation to be 0. And in that sense, so if this is be equal to 0, and then I introduce that back into the original deformation equation here, then I'm going to end up with saying that, you know what, the deformation is going to be equal to d plus, times this other stuff. No, but this is not enough to say, okay, how much is the deformation? Because I'm still, I don't know how much is d. I need to get rid of that d. But I do know other boundary condition that I said, it might be tricky, but yeah, it was tricky at the beginning, but I now realize that I need that boundary condition, as that when x equal to L, meaning in this point, y is going to be equal to d. And then when I substitute that in that kind of place, I'm going to end up again with these kind of situations, that the cosine of this has to be equal to 0. And having that, then again, postulates the same kind of results, that, the solutions to that problem is infinite. And then I just take the minimum probable value that could fulfill that solution, and that's going to give me this other equation according to this load. Now I want you to, let me check something, but I just mentioned in the other case, other two. Yeah, but I want you to compare this equation here with the first one. Let me bring the first one. This one here. Look at this. This is for a pin condition, and this is for a fixed free condition. As you have already noticed, the main difference lays in the denominator of these two equations. The first one being for the pin condition, L squared, the second one being for L squared. Meaning that physically, or from an engineering standpoint, the creeping load for a pin-pin condition is going to be always larger than the creeping load found for the same column characteristics on a fixed free condition. Because you see here that this 4L squared, this 4 dividing this whole term, is going to make this number smaller, meaning that for the same under the same loading conditions and geometrical conditions of the column, meaning height of the column or the length and section properties, these cases are going to require less force to buckle than the other case. Then it might be possible, that's why when we see such configurations as in this one, that columns are maybe larger in section, in the area, than these ones, even though this is not a great example because it's failed, but it is typically that when you have maybe these pin-pin conditions, even though these are fixed, but pin-pin conditions, the way they are smaller, let's put it this way, than this one here, because of this condition that you need less load to buckle a fixed free column than to buckle a pin-pin column. Now, interesting to see that, let me bring these two equations actually. When you see the other two cases, this is for the both end fixed. Let me move this a little bit. And my computer is not responding now. Okay. This is for a fixed condition, and look at the way it deforms, because now they have a resisting moment because there are no degrees of freedom in the joints that allow the column rotate around these 2 points, but they are constrained in all 3 axes if we look at it from the planar case, meaning they cannot move in either translational directions or rotate, meaning they are just fixed, and this is the way they're going to deform. And it's interesting to see, if we look at this picture again, that this is clearly a fixed condition, that look at how it kind of course there is a deformation here, but how the buckling happened in the middle of the section mainly, and that's very well aligned with the way the buckling is described to happen for a fixed uh, column. And this is also a representation of what a fixed column is. The formula to determine the buckling load or crippling load for this configuration is found as this. Now, let's compare between these 3 cases now. So we say that pin, which is this one, yeah, let's call it, this is the baseline case, meaning that's our reference case. If we consider the fixed free, what I said was that it requires less load to produce buckling in the column. Now, if I come to this case here, what this says is that it requires now more load to produce buckling in the column, according with respect to the reference case. So this is fixed, meaning that if I'm using a fixed column, the load needed to produce buckling in that column is going to be higher than the one needed for the pin case. How things are appearing right now. And we're going to finalize. I want to thank you for agreeing to this schedule. We'll continue next week, but soon to finalize according to the class. When I looked at the fixed pin end, this is the result I'm going to have. And now what the result is saying is that the load to produce buckling under this ending configuration is going to be larger than the reference case, but it's going to be smaller than in the fixed case. This is interesting. So as engineers, depending on how you choose to join the columns to the other members, you're going to have either certain resistance to buckling, let's call it that way, that's going to be large compared to the reference system, or it's going to be smaller. So as your choice to join, not only because of loading, but because of structural integrity and other requirements, but depending on that, you have the decision. It's in your hand to select, okay, how would you like to handle these cases, knowing that if you're going to choose a fixed condition, the buckling strength, let's call it that way, is going to be larger than in the fixed free condition. That's amazing. That's simple yet powerful, because it is in our hands to decide this kind of stuff. Now, to unify the formula for Euler column calculation, there is something called effective length of a column. And it simply takes these cases here, this one, and this one, and tries to unify them into a formula that we can learn easily. We know that the crippling load or buckling load, according to Euler's, is this one, where this L here, this big L, is going to be considered, or it's going to be the effective length of the column. And depending on the loading case, that L is going to be a half bit, a half of kind of L divided by 2, or well, and so on, some others kind of, or for example, when is this case that is kind of pin and fixed is going to be this. And what it does is when it has the, for example, the pin case here, what it says that this L, this formula is going to be pin is going to be transformed into pi square AY divided by L square, which is the same reference case. But imagine that it's not pin, but it's kind of, fixed. And then if it's fixed, then this formula is going to be fixed is going to be P equal to pi square EI. And then this is going to be L square. L square is going to be L divided by L square divided by 4, which is going to transform in 4 pi square AI divided by L square, which is the same representation we have here. And these are the cases we're going to use, these 4 cases, this, and this. And if you hang on a couple of minutes more, Euler, we said that it only works for long columns or certain slenderness of the column. And that slenderness is defined as such. For example, let's take this one here, this graph here. If I plot the Euler's formula, it's going to give me this red line here. Well, let me just put it. It's going to give me this red line here. But this is going to be asymptotically approaching the vertical axis, and it's not, from an engineering standpoint, something that is practical. So if we consider 330 megapascals as the yield strength of the material, and I kind of cross a horizontal line here, and when that horizontal line intersects the Euler hyperbola, I think it's called, in that point is where I'm going to know that Euler starts working, meaning that when you determine this point here, from this point on is where Euler is valid, let's call it in that way, or is considered valid. Because you cannot use Euler all the way completely to here, because then you are going to say that, well, according to Euler, this column has a, the crippling load is 500 megapascals. Yeah, but but the material is only 330 megapascals, so it's going to fail by yielding. So Euler is not valid in this region. So that's why if you attached or you just add this horizontal line here representing the yield stress of the material, and when it touches that, you say, well, this is where Euler is valid. Besides that, well, maybe you better work with crushing stress, which was why kind of what we said here in this formula, that depending on the type of column you are using, is either failed by crushing or by buckling, or buckling and crushing. So in that sense, this presents a very nice representation of when Euler's work and where not. And then if I take these 330 megapascals and you're going to find out these calculations very easily to follow up, is that at a slenderness ratio of 80 is the critical point where it says, well, you know what, after 80, whatever column you have, you can use it for this material, but before that, you might not use it. and this falls within what is our kind of these medium columns, where we said that they could fail either between by crushing or by buckling. So this is one of the ways to determine, hey, you know what, uh, after 80, so this material you can use Euler. Before that, no, don't use it. Just use the crushing stress. And well, guys, I'm going to leave you until this today. And next week we're going to continue buckling of columns, and we're going to do some brief exercise just to explain the theory and to fixate kind of those concepts. What questions do you have? None. If not, I wish you a very nice weekend. Take care. And as mentioned in the announcements, I will be taking care of next week exercise sessions. And the reason for that is because I want to emphasize a couple of points related to the formation of beams and kind of the Macaulay's method. And I'm going to give you some specific insights that are going to be useful for you. Then, if nothing else, I would like again to wish you a nice weekend, nice rest of the week. I'll see you on Monday and Wednesday via Teams. Remember that. And well, take care and goodbye.